Hey everyone, and welcome back to the channel. Today we're diving deep, literally, into one of Earth's most explosive secrets. What's hiding beneath supervolcanoes like Yellowstone? We all know the stories about Yellowstone's massive caldera and the potential for a super-eruption. It's a bit scary, right? But what if I told you the story is way more complex and fascinating than just a giant pool of magma waiting to blow? Most of us picture a supervolcano as this enormous underground cavern filled with molten rock, like a giant angry pimple on the Earth's surface. But that image is actually a bit outdated. Scientists have been using some seriously cool tech, like seismic tomography, which is basically like giving the Earth a CT scan. And what they've found is shaking up everything we thought we knew. Instead of one single giant magma chamber, the reality is more like a massive multi-level plumbing system. Think of it less like a balloon and more like a sponge. Down deep, we start with what's called a mantle plume. This is a colossal column of superheated, buoyant rock rising from deep within the Earth's mantle, maybe hundreds, even thousands of kilometers down. It's the engine driving the whole operation. Now, this hot rock from the plume isn't entirely liquid. It's more like a slushy, a mix of solid crystals and molten rock, what geologists call mush. As this mushy plume rises, it hits the base of the Earth's crust, which is much cooler and more rigid. Here, the heat from the plume starts to melt the surrounding crustal rock, a process called ponding. This creates a vast, deep reservoir of this hot, crystal-rich mush. For Yellowstone, this lower reservoir is gigantic, estimated to be about 4.5 times larger than the upper chamber we always hear about. It's located about 20 to 50 kilometers beneath the surface. But again, it's not a big pool of liquid. It's mostly solid, with only about 2% of it being actual liquid melt. So, where does the eruptible magma come from? Well, within this deep, slushy reservoir, the lighter, more liquid parts of the magma slowly separate and rise, a bit like cream rising to the top of milk. These blobs of more purely molten rock then ascend further, collecting in a shallower magma chamber. This is the one we usually associate with Yellowstone's volcanic activity. It sits much closer to the surface, maybe 5 to 16 kilometers down. This upper chamber is also not a giant lake of lava. It's another mush zone, but a bit wetter than the one below. Estimates suggest it contains anywhere from 5 to 15% molten rock. It's still mostly solid, like a sticky, crystalline sponge soaked in liquid magma. This is the magma that has the potential to erupt. It's richer in silica, which makes it very thick and gassy, the perfect recipe for an explosive eruption. So the whole system is a complex, vertically stacked series of reservoirs. A deep mantle plume feeds a huge, mostly solid lower crustal mush reservoir. From there, more refined magma trickles upwards to feed a smaller but more melt-rich upper crustal magma chamber. It is this upper chamber that fuels all the amazing geothermal features we see at the surface in Yellowstone. The geysers like Old Faithful, the hot springs, and the bubbling mud pots. They're all powered by the heat from this relatively shallow body of magma. But what triggers a super-eruption? It's not as simple as the chamber just getting too full and popping. It's a delicate balance of pressure, temperature, and chemistry. One leading theory is called magma recharge. This happens when a fresh, hot batch of magma from the deeper reservoir is injected into the shallower chamber. This new injection acts like shaking a soda can. It rapidly increases the temperature and pressure, and the new, hotter magma can cause the gases dissolved in the existing magma to come out of solution, forming bubbles. This bubble formation, or exsolution, drastically increases the volume and pressure inside the chamber, potentially fracturing the overlying rock and paving the way for an eruption. Another factor is the crust itself. The weight of the rock above the magma chamber acts like a lid, keeping everything contained. But over time, geological processes like tectonic stretching or faulting can weaken this lid. An earthquake, for example, could potentially crack the rock above the chamber, providing a pathway for magma to escape to the surface. It is a complex interplay between what's happening below and what's happening in the crust above. The amazing thing is, scientists can monitor this entire system. They use GPS stations to detect subtle changes in ground level. If the ground swells, it could mean the magma chamber is inflating. They use seismometers to listen for tiny earthquakes, which can signal magma moving around underground. And they analyze the gases coming out of fumaroles and hot springs, because changes in the gas composition can hint at changes in the magma below. So while the idea of a supervolcano is still incredibly powerful and a bit intimidating, modern science gives us a much clearer and less movie-like picture. It's not a ticking time bomb, but a dynamic, breathing geological system that we are constantly learning more about. The structure is more like a series of interconnected slushy sponges than a single giant tank of lava, and understanding this complex plumbing is the key to forecasting its future behavior and keeping us all safe. Think about it. This same process, this mantle plume and multi-stage magma system, is responsible for creating some of the most dramatic landscapes on our planet. The Yellowstone Snake River Plain is a perfect example, as the North American plate has slowly drifted over this stationary mantle plume for millions of years. The plume has essentially burned a track across the continent, triggering a series of massive caldera-forming eruptions along the way. Yellowstone is just the current hotspot on this ancient trail. This deeper understanding also helps explain why super-eruptions are so rare. You need all the conditions to be just right. You need the mantle plume to be active. You need the magma to differentiate and collect in a shallow chamber. And you need a trigger to overcome the immense pressure of the overlying rock. It's a geological perfect storm that only happens on very long timescales, so the next time you see a picture of Old Faithful, don't just see a geyser. See the very top layer of an immense, intricate, and powerful heat engine that connects the surface all the way down to the Earth's deep mantle. It's a beautiful reminder of how dynamic our planet is, constantly changing and reshaping itself from the inside out. The world beneath our feet is far more complex and wonderful than we can imagine. Thanks so much for joining me on this deep dive today. I hope this gives you a new perspective on the incredible forces that shape our world. If you found this interesting, do me a favor and hit that like button, and be sure to subscribe and ring the bell so you don't miss our next adventure into the wonders of science. Let me know in the comments what other massive science topics you'd like me to break down. Until next time, stay curious.